Hey, Grace, can you stay at the end of our review for like 2 minutes so we can just discuss your email and everything?
Yes.
No big deal. Thank you.
Yeah.
All right. Okay, so I'm lecturing from my iPad, and so if someone pops in after we start, I won't be able to see them. So if anyone like is joining and panicking, I'll just try to pop back and forth. But if you see someone trying to get in, or your friends are like, "Oh my God, Dr. Pappas, where are you?" Let me know. So we're going to talk for an hour. I'll answer questions, and let me screen share, and we'll be ready to go. Can you all see my notes?
Yeah.
Yes.
Cool. What do you want to know?
Can we go over all the equations we need for separation just to double check I have them all written down correctly?
Oh, yeah, okay. That's a lot, okay. So we'll start with capacity factor. That's going to be equal to the retention time of your peak minus the mobile phase time divided by the mobile phase time. So that's a unitless parameter, right? And I'm just going to draw time and signal here. So you're going to have like, various peaks, right? This is like your mobile phase time. And then each peak has its own retention time, right? There is plate height, which is the length of the column, which is given, divided by the number of theoretical plates. And the number of theoretical plates equal to 5.54 times 10. Nope. What am I doing? Okay, 5.54. Sorry, I was doing something totally different. Times the retention time squared divided by the half width squared. So that's also a unitless parameter. Plate height has units of length, but plates has no units to it. Okay. There's resolution, and that's equal to 0.589 times the difference in retention time over the average half width. And then there is the mobile phase flow rate is equal to the length of the column divided by the mobile phase time. The analyte migration rate is equal to the length of the column divided by the retention time for whatever column. So remember, each peak has its own retention time, its own half width, its own plate height, and its own number of theoretical plates. Okay, and each pair of peaks has its own resolution. Okay, and then don't forget one last equation, that the analyte flow rate can also be expressed as a function of the flow rate of the mobile phase times this F term, which is the fraction of analyte in the mobile phase. So 7 equations that you should know.
Should we also know the equation for the fraction that F equals Nm over Nt?
I mean, you're not going to have to calculate, but it's a fraction of material in the mobile phase, which is the number of moles in the mobile phase over the total number of moles. But you don't have to really know it per se. You don't have to calculate.
Thank you.
Yeah, no problem. Should I periodically check to let people in? So, what else can I help you all with?
Dr. Pappas?
Yes.
So in tandem separations, if the stationary phase is nonpolar and the mobile phase is polar, would size elute from smallest to largest in that sense?
No. Okay. So, I'm glad you asked that question. Okay. All right. For tandem separations, I gave you an example of polarity and size, but you use 2 separation methods. with different, how would I say this? Different separation parameters, or separation modes. So, for example, here are the modes that you have available to you in the different types of separations. You can separate based on polarity, and of course, that polarity can be, depending on if your solvents, if your mobile phase is polar and your stationary phase is nonpolar, or the reverse of that, right? That order will change. You can base it on size, right? You can base it on charge. You can actually separate based on mass to charge. What else can you do? Hydrogen bonding. So you can pick a bunch of different, trying to think if there's anything else I'm missing. Size, charge. These are the major ones. pKa for acids. You can also separate based on pKa. So you can pick any one of these and pair it with another one to get tandem separations. So in class, I gave you an example of a polarity and a size-based one, but you could separate based on charge and on pKa, for example. Right? As long as it's two different methods, then you'll get the advantage of doing tandem separations. Make sense?
Yes.
Okay, great.
Dr. Pappas,
Yes.
can we go over quadrupoles or kind of like the main takeaways that you will be looking for or like asking us, please?
Yes. I'll talk about the quadrupole and the quadrupole ion trap. Sorry, my handwriting is garbage today. It's always garbage, but it's like extra garbage. Okay, so quadrupole ion trap. You don't need to know its function. Like, you don't need to know how it works in the sense of like what the poles are all doing, right? And if you want to think about it, it's essentially it's four poles. I'm gonna just go ahead and draw them three-dimensionally. Okay. And you have an ion, and only one of the ions gets through, right? To illustrate what happens, every other ion that comes in, every other mass to charge, right? So the different colors, different M over Z, will hit a plate or hit a pole, and they'll stop. Excuse me, everybody, for coughing into your microphone. So any other mass to charge hits it, only one makes it through, all right? So that's the general function you have to worry about. What I really want you to know, though, more than that, are the sort of fundamentals of the concepts. So the concepts I want you to know, they are small or compact sources or compact mass analyzers, which is good for like building portable instruments, small instruments. They are low resolution. In other words, they're not high resolution like Fourier transform instrument. And they have a limit of about 5,000 M over Z, right? 5,000 Daltons. And I mentioned before, we get around that if you use electrospray ionization. Z is high. So you can look at larger ions that way. Like a larger molecular weight ion, like, if it's 100,000 Dalton protein and it has 100 charges on it, which is not out of the question for electrospray, then its M over Z value is 1,000, which puts it well within the, less than 5,000 M over Z range that a quadrupole can use. So a lot of times you'll see quadrupoles using electrospray sources to look at big molecules that way. That's what you need to know about quadrupoles and quadrupole ion traps.
Okay, thank you.
Mm-hmm. Of course. So check see if anyone's waiting in the Zoom. Oop.
Dr. Pappas, do you mind going over the mass defect concepts again, please?
Absolutely. Hold on. Yeah, let's talk about mass defect. Okay. The idea behind this is I'm going to use lithium-6. Okay. And I'm going to. So a lithium-6 nucleus is composed of a couple things. It's going to have 3 protons, 3 neutrons. I'm going to color them because you know me. Okay, so this proton and neutrons, they're in very close proximity, right? So there is a repulsive force due to Coulombic charge, right? And obviously the nucleus doesn't fall apart. So there's got to be a cohesive force that's keeping it together, and it's got to be greater than the repulsive force. Otherwise, the nucleus is unstable and just flies apart, right? So this cohesive force is called nuclear binding force, right? You need nuclear binding energy to produce this force, okay? That has to come from somewhere, and so it actually comes from the mass converts into energy to keep the nucleus together. What does that mean in mass spectrometry? If I had a scale, I'm going to draw a scale if you don't mind. First, I want to copy my nucleus. I'm really proud of it. Okay. If I have a scale or a balance, fulcrum on it, right? Sorry, guys, I'm having to tell my daughter to shut up, and now my son's screaming. They're just being buttholes, right? If I have, hold on, everybody. I'm going to pause for. Can y'all hear me okay?
Yes.
Yeah.
Sorry, I had to leave and go into my garage because my family does not understand the concept of I'm teaching. All right, so if I take individual protons and neutrons, right, versus the bound nucleus, these actually weigh. Oh, what just happened? The individual parts weigh more, and the bound nucleus weighs less. If you take apart the nucleus, it would actually, the masses would convert back to their higher values. Only when the nucleus is compressed together that it gets lighter. And so in nuclei, protons and neutrons get lighter. It's actually the neutrons, but we don't really know that for sure, right? What does that mean? It means the if I look at, I used methane before, and I'm going to use methane again, if that's okay. Actually, I'll use ethanol. Right? This has a mass of, let's see, this is 15, this is 14, and this is 17, which gives me a total mass of 29 and 17. I can't do this in my head, I'm really sorry. 46. Okay. Point something. Right? If I do this exact same thing, but let's say I don't know if this molecule can even exist, right? Actually, I'll keep it there, okay. Let's say I do this instead, though. Let's say I make this molecule. So I replace hydrogen with the deuterium, right? It would be 47.xyz, but, or I should say ABC. So the ABC and XYZ are decimal places, and I'm giving them different values because they're not the same, right? So like the XYZ decimals aren't the same as ABC. If I then replace, if I go back to this molecule and I make this a carbon-13, and I go back to a hydrogen, this is still, basically it's plus one neutron heavier, right, in each case. It's going to be 47 with different decimal places. So even though only one neutron is added, the mass is different. And just to explain this one, or give you one more example, if I was to do this, so put a deuterium here, it would be 47.ABC mass. It would have the exact same mass, in fact, as my case here, where I just put a deuterium instead of a hydrogen. The deuterium has the same mass no matter where I stick it on the molecule. It's the fact that I put a neutron in the carbon nucleus versus the neutron in the hydrogen nucleus. It gives it a different mass value because the binding energies are different. Does that make sense?
Yeah, that makes perfect sense. Thank you so much.
Sure, sure. What else can I help you guys with?
Professor,
Yeah.
can you go over the main free path?
Yes. So I'm going to start with my analyte molecule. Okay. And in yellow, I don't think it shows up yellow or not. Okay for y'all. Sorry. These are other gas molecules or atoms. Right? The mean free path is how far it travels without a collision. Now, if you think about it, if the mean free path is greater than the entire ion flight path, in other words, from source, there's the mass analyzer, right? And there's a detector. So that's the whole ion path, if you will. If the mean free path is greater than the ion flight path, then on average, there are no collisions at all, right? Because it actually travels the entire distance and it would do so without a collision. In tandem mass spectrometry, we actually shorten the mean free path in certain areas of the mass spectrometer in order to actually make collisions happen, right? So the shorter the mean free path, the more collisions that it has per unit length. Make sense?
Yeah, it makes sense. I have another question, if you don't mind.
I don't charge per question, so ask away.
Okay. It's actually a question on like one of the practice questions.
Mm-hmm.
And it's about the fragments, like
Which year and which exam?
the exam.
Do you know offhand? I have them in front of me, so.
Yeah, in front of me, in front of you. Okay, it's actually a practice question that you posted on April 18th.
Oh, it's one of the. Okay, give me a second then.
Okay.
Sorry, I didn't have those. I had the exams, but let me see. Practice questions 2, right? Okay. Hold on, it's opening. Oh my god, it's taking forever. Okay, what's the question while I'm waiting for it to load?
All right.
Yeah, sorry.
So it's the first question. It says, consider the following structure. Which fragment?
Wait a minute. Okay, let's go through this.
Yeah.
Wait, this one? The practice questions 1 or 2? I guess it's this one, right?
Yeah, this one. And
Yeah, okay.
Yeah, the 1st question.
Let's go through this. Okay, so this is a structure of bromobenzene, and I ask what fragment corresponds to a loss of 79 and 81 Daltons. So there's the molecular weight, and it loses 81. Okay. 79 and 81, actually, technically. All right. If you look at this molecule, let's just really quickly, in different colors, highlight some of the stuff about it. Okay. It's got double bonds, right? And I put those in green. It's got, even though they're not shown, it's got 5 carbon-hydrogen bonds, right? And it's got 1 bromine hydrogen or bromine carbon bond, right? So there's a CH bond, there's C double bond C, and there's CBr. Okay. Starting with the carbon-carbon double bond, do you expect that to be a strong bond or a weak bond?
Strong.
Yeah, it's going to be pretty strong, right? You might not know about hydrogen, but if you look at hydrogen on an IR spectrum, actually it doesn't even show up in the IR, it has to be a Raman spectrum. It's at 4,000 wave numbers, which is a really energetic stretch, so also strong. But the carbon-bromine bond isn't going to be strong. Now, you could be telling me at this point, well, geez, Dr. Ibris, I didn't know. How would I know, right? I haven't been a chemist as long as you or whatever, right? So let's look at this. Let's look at how we would really solve this. But we know we're going to break a bond somewhere, and you're not going to likely break a double bond, right? We know that. So if we break a carbon-hydrogen bond, how much mass is lost if you lose a proton? 1, right? So let's look at, we're probably going to break this carbon-bromine bond, and let's look at the structure. So if you look at this structure by itself with 5 hydrogens on it, right? So there's a bond broken here. We can figure out this mass. It's 7 times 12 plus 5 times 1, or 77 Daltons, right? So this part of it is 77. So by default, this has to be not 77. Now, 77 and 81, there are 2 bromine isotopes, 79 and 81, which you could have looked up. But even if you didn't know that and you looked at it, it tells you it's got a mass of 80, which is plus or minus 79 and 81 is 80 on average. And then it can't be the rest of it because that's 77. Make sense?
So it's based on their mass number?
Yeah, let's do another one. That might be not as tricky. Okay. I got to think about it because last time I did this for a student in my office, and I picked isopropanol, which turns out to be like the worst possible choice. So Anybody know what this molecule is? I mean, I know. I'm asking. I'm just curious if you know.
Butanol.
It's 1-butanol. But yes. All right. So it's got chunks, pieces, right? You can kind of look at functional groups, right? That's how we think about this. So this is 17, 14, 14, 14, and 15. Okay. So I was drawing its mass spectrum. Its total mass to charge is something I can't do in my head. 14 times 3 plus 15 plus 17. It's got a mass molecular weight of 74 Daltons, roughly, right? And some change, but we're in a round, okay? So its parent peak, the parent ion, M+, is going to be at 74 Daltons. We're not going to break CH bonds, right? We're going to break carbon-carbon bonds and carbon-oxygen bonds, and we're going to break single bonds more than double bonds, and there are no double bonds in this molecule, right? So you might see a peak, for example, I'll draw a couple peaks here. You might see a peak at, let me do this math in my head. I don't want to screw this up. 59. Is that right? 59? I wrote 57, didn't I? Hold on a minute. Okay. Sorry. You'll see a peak at 59. You'll see a peak at 57, possibly. Right? You'll see a peak at 45. And maybe a peak at 31, right? So here's your mass spectrum. Can we figure out what all these different parts are from, right? And we actually can. All we do in a mass spectrum, really, I mean, like, you would do this if you worked like in Dr. Meshroff's lab or something like that, is you would take out, a pen and measure the mass difference between all of these from the parent ion, okay? So this first one, and I'll put it like in blue ink here, this first one is a loss of 15. This is a loss of 17. This is a loss of 29, if I'm correct. And, hold on. This is a loss of 43. Okay, so that's what we've lost to get to these values. And so you can now look at this molecule and ask yourself, okay, it's 74 Daltons. I'm probably going to lose, I'm going to lose a functional group on the edges of the molecule versus like the internal structure of the molecule first, right? So what functional group has a mass of 15 that likely fell off to produce an ion? To produce the 59 Dalton ion.
The methyl group.
Yeah, you would lose a methyl group. So it would be CH2, 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 OH plus, right? So you lost the methyl group and made that ion. In the case of the M over Z 57 ion, what do you think you lost? You had to lose a mass of 17.
The OH bond, or the OH group.
OH. OH is the only thing that adds up, right? So that would give you a structure that looks like this. And you'll notice it doesn't make sense, right? Like the carbon doesn't have the right charges and everything. That's okay. These are gas phase ions. They don't play by the organic rules that you learned, right? Moving on to the 45 peak, right? What did you have to lose? You had to lose 29. So what functional groups add up to 29?
The methyl group and the CH2 group.
Yeah, one methyl and one ethyl, right? So you would have lost a CH2 and a CH3, and that gives you basically a structure of CH2, CH2, OH plus, right? So you can lose functional groups or you can lose pieces, like groups of functional groups. I don't know if there's a better word for that, I guess, right? But like, you know, a larger grouping of functional groups, if you will, right? And then that 31 Daltons, you can look at it two ways. You can look at what fell off, or you can also see what was left behind, right? But what would give you a structure of 31 Daltons? Like what functional groups add up to OH? To OH, I gave it away partly. Add up, right? It's going to be CH2OH plus. So you really just look at the molecule, you break up the functional groups and get their masses, and then you see which pieces of those add up to this group. Don't get creative and suddenly start like making structures that don't exist, right? Just kind of chop off pieces of the molecule. If you chop off this piece, you've lost 15, you've retained 59. If you chop off this piece right here, you've lost 17, you've retained 57, right? Make sense?
Yeah, that makes sense. Thank you.
Cool.
Dr. Pappas,
Yeah.
I think there's someone in the waiting room waiting to be let in.
Oh, well, let's see who it is. Yeah, it's Becca. Thanks. Okay. What else can I help y'all with?
If nobody else has a question, can we go over time of flight real fast?
Yeah. What about like? I was doodling. Okay. Flight. You mean just like all? Let's walk through a time of flight experiment, if you will. Okay. There's going to be two parts of this experiment. There's the ion source. And then there's the flight tube, the detector at the end. And this flight tube has no electric field. Okay. So what happens is we've got like our MALDI spot. And a laser fires onto it, a UV laser. Okay. When that happens, of course, you start to eject ions into the gas phase, right? Like the laser fires and you create a cloud of ions. Now we know that in post-source decay, we let them bounce around a while and fall apart. But what we do in time of flight is we accelerate our ions across this region. So I'm going to blow this up for a second, okay? So you've got the entrance to the flight tube. You've got your matrix crystal. You just fired your laser, and so now you've got a bunch of ions floating around, okay, near the surface. You turn on the electric field in the ion source. And so what happens is you accelerate these ions through that distance. Okay, you apply a force. It applies a Coulombic force, F of C, and over a distance. Which I will call D. So there's a distance from the matrix itself to the exit of this ion source, the entrance of the flight tube. And if you remember your physics, force times distance equals work equals energy, right? In this case, though, it's kinetic energy. So what you've done, essentially, by turning on that voltage, is you've taken all of the potential energy of that ion and converted it, right? So they all get accelerated from the source into this region, right? Once they're here and there's no more field, you've got ions of different size, okay? all of the same charge have the same kinetic energy. Right? So remembering that, so here's your flight tube. Here's your detector. You've got an ion and a bigger ion, right? Ke, kinetic energy, which you got by applying force over a distance, is equal to 1/2 mv squared. So larger ions, or larger m over z ions, have slower velocity. This is constant, right? So if you increase one, you have to decrease the other, and vice versa. And so if you're looking at this from a vector perspective, your smaller m over z ion is faster, and your larger m over z ion is slower, which is totally intuitive. And so if you're measuring time and signal, right? Smaller m over z arrives first, larger m over z arrives later, and then we calibrate that using standards to produce a mass spectrum, m over z, and signal, right? So you would get peaks as a function of time, let's say. So I'm trying to draw the same peaks. We just convert it to a mass over charge scale after we measured the time.
Dr. Pappas, would you mind scrolling the page just a little bit?
I'm sorry, I can't hear you. Can you repeat that? Like it's barely coming in.
I said, would you mind scrolling your page up a little bit?
No, I'm not gonna. I'm just kidding. Yeah, of course. How about that? More?
Yeah,
Is that good?
Yeah, perfect.
Okay.
Yeah, that's good.
Yeah. I'll post these, by the way, probably after I have dinner tonight. But I'll post all these notes as well.
Dr. Pappas,
Yeah.
can you go over moldy?
Yeah, I will. Okay, so this is matrix assisted laser desorption ionization, if you remember it. And the way it works is the following, right? There's going to be like an electrode surface, because we need to apply a voltage later, right? This is different than like electrochemistry. And we start off with like a droplet. This is a terrible droplet. I'm going to redraw it, right? A drop of organic solvent. That's my matrix. My matrix has two jobs, right? One of them is to dissolve my analyte. I'm going to make my analyte just be like little green circles here in my sample, okay? We let some time pass, and what happens is our droplet dries into a film. It makes a crystal as the droplet dries. Okay, so now if I look at that, let's put it here. All right, so there's my droplet now, okay? Like, so all I've done at this point is I've taken my sample, I've dissolved it into my analyte, and I dry it into a droplet. Now, I'm going to need to get a little creative here for a second. I need to copy this a few times. Okay. Okay. Now what I do is I take a laser and I focus a laser beam onto the surface, like a pulsed laser. And all of that energy is absorbed in a very small region very rapidly. And so what happens is I actually create like a little explosion where my matrix molecules fly out, right? They kind of explode from the surface outward. So the laser fires in step 3, and then in step 4, like a nanosecond later, you get an explosion from the surface. And in this explosion, you get clusters of matrix molecules, and your analyte also gets blown out into the gas phase in ionized form. So the whole point of the matrix is to absorb. The matrix dissolves the analyte. The matrix crystallizes. And then the matrix absorbs laser and explodes. And that's how you get very massive molecules into the gas phase. And then it goes into, so this is separate, to the time of flight. Like you would turn on the voltage on the electrode surface, and then you would accelerate your ions into the mass spec after that. Does that make sense?
And you said that the matrix is always paired with the time of flight.
MALDI, MALDI,
Yeah.
I mean, okay, I don't want to say always, because I've seen a couple weird cases where, like, you know, I've seen like MALDI attached to a quadrupole, but like in weird instruments. If you're going to encounter one commercially, they're always together. And the reason for that is MALDI makes large, intact M over Z ions, right? Large M over Z intact ions. So the mass to charge ratio of ions produced in MALDI can be hundreds of thousands of Daltons, even up to like a couple of million Daltons, giant molecules. And the other mass analyzers can't handle ions of that size. Time of flight can handle any size ion because it's limited by how long you wait for the ion to traverse the field. And we're talking about far less than a second to complete an entire mass spectrum of all possible mass values.
So then is the drawback to this machine the size of it compared to something like a quadrupole?
Well, I mean, it's certainly bigger than a quadrupole. So, and you don't need, you know, if you're going to use a quadrupole, you're talking about lower M over Z ions. So you wouldn't necessarily use this, you know, a time of flight because it's made for high over M over Z ions. So in other words, if you're looking at like, you know, organic products and you're talking about under 5,000 Daltons, there's no reason to use a much more, you know, sophisticated and much more expensive piece of equipment when you can use a quadrupole, right? On the other hand, if you want to look at like an intact protein, you can only look at it through time of flight. And so you would use quadrupoles when you want like a, you know, a more simpler or more portable approach. Time of flight would be, you know, high mass range, and then you'd use like an ion cyclotron or orbit trap when you want high resolution, essentially. In fact, while I'm talking, you know, one of the reasons I didn't ask about electromagnetic sectors, like in double focusing, is they're not really that common anymore. Like in our department, if you start knocking on doors and asking about mass spectrometers, they're either going to be quadrupoles, quadrupole ion traps, triple quadrupole, or orbit traps. That's all you're going to find in our department, and we have a lot of mass spectrometers.
Dr. Pappas,
Yes.
do you mind going over the Faraday cup?
I don't mind, although mass spec detectors aren't on the exam. So I bet no one else wants me to go over it. So if you want me to, I could talk about it afterwards, but it's not on the exam.
Okay,
up to you.
that's okay.
Okay, I figured, but I thought I didn't want to stifle your intellectual curiosity. But yeah, there's no mass spec detector question on the exam.
I don't want to hog, but if nobody else has a question, can we go over like the Van Diepter and what to expect on it for the test?
I mean, I'm not going to say what to expect necessarily, but I'll talk about Van Diepter. I mean, anytime. You guys know how I feel about it. And you don't have to worry about hogging questions. Oftentimes, people are glad you asked the question. Like, I mean, no one's ever come to me and been like, "Oh, student X is the worst for hogging all the time." So let's look at the Van Diepter equation. Okay, it dictates what plate height should be, and it has three terms, two of which are related to the mobile phase flow rate, and one is not. Right? There's the multiple path term, which is not related to flow rate. And that's just how we'll talk about in a minute. There's diffusion. And last but not least, there's mobile phase, stationary phase equilibration, right? So this equation will then give you plate height as a function of mobile phase flow rate, like this, right? There's going to be essentially three sections of this curve. There's going to be a negative slope portion, then sort of a DC or flat portion, and then an increasing region, right? The multiple path term is the flat part of the curve. The diffusion term is the negative slope. And the mobile phase, stationary phase equilibration is the positive part of that slope, right? So that's where each part of that equation contributes the most. If we look at these terms, right, A is proportional to the particle size. That's what you really need to worry about, right? And there's no flow rate component. So at any flow rate, A is the same, right? The B term is inversely proportional to time. So the longer you go, the worse. Well, let me get that right. Hold on a minute. Nope. That's inverse for to U, not time. It's easy to get turned around on these things. So the faster you go, the better diffusion is going to be. It's going to be smaller. We want diffusion to be small, right? So B is proportional to time. So that means that slow separations, slow peaks are bad because you get band broadening. And it's worse than a faster peak. Okay. Then there's this C term. Well, C has two components. It's actually a stationary phase and a mobile phase component. The stationary phase component is proportional to the particle size. Say that backwards. But it doesn't really matter either way. Right, so you have two terms that are proportional to particle size and one term that is not. All right, so if you think about it, if you break down this equation, the A term is not related to U, right, at all. The A term and the C term are related to particle size, and then the B term is not, right? So this tells us a couple things. First and foremost, what I'm going to highlight in gray here is the optimal rate to work at. That's a U. I'll redraw it. Okay. Anywhere from here to here gives me a low plate height. If I try to go faster, if I work out here somewhere, right, I have a higher plate height, which means at higher flow rate, there's mobile phase, stationary phase equilibration. That's giving me bad band broadening. If I work out here right, I'm going to end up with diffusion being the major limiter, right? So if I go faster, because this is a slow flow rate, if I go faster, the diffusion doesn't become as big of a deal, and then multiple paths is the major part of the term. And as I go faster, I start to leave behind my material in the stationary phase, which makes my band broadening bad again, right? So this is the Van Deemter curve and how it changes. Now, what if you made a larger, what if for some reason you bought a new column, okay, and it has larger particles, right? What would that look like? Well, diffusion would be the same, right? Your multiple path term would be worse, and then your C term would be worse also. And so not only is your total plate height worse, but your optimal range of flow rates is smaller, right? And if you had like really big particles, it actually would look like that almost, right? So your optimum range is right there and it's pretty small. Does that make sense?
Yes, thank you.
Mm-hmm. We've got a few minutes more for some other questions if y'all want.
I think that's probably it.
All right, our spokesperson said it. If there are no last questions, then I'll see y'all tomorrow, and we'll have a one more mini exam. Like I said, I'm going to have your grades. I'll have your grades done on, I guess, Tuesday. So don't panic on Monday if you look at your tests and you're like, oh my God, because there are some of them I have to go through and manually grade. It won't take very long. And so, yeah, I'll see you in class tomorrow at 11, right? Grace, again. Yeah.
It's not like you don't have to go over any questions, but in class on Friday, you mentioned possibly going back through your old